outlook.com. I spelled that correctly, full stop there. Okay, but feel free to just, whenever you want to, just sort of drop me a line. And Mustafa, hello. Good to, I don't quite know what the expression is. Should I say, it's nice to see you engaging with the session, even though I can't see you. And I don't think I've ever seen Mustafa. Never seen you before. And I certainly haven't seen Ahmed. And I think it's a bit late probably to start turning on webcams, but I don't know whether either of you have seen me, but I could show you on the webcam, but my webcam at the moment is dedicated to watching a little sketch pad in case I need to do any diagrams. So, Mustafa, thank you very much for asking me how I am. I'm feeling very, very tired at the moment because I travelled back from North Wales last night and didn't get back until about midnight, and I was actually driving for about 9 hours through the mountains and windy roads. So I enjoyed being there very much. It's a lovely, lovely place, and if you ever get the chance to go to North Wales, do go and see Mount Snowdon. And if ever I think, Mustafa, you're in London anyway, but if you want to travel to North Wales, Ahmed, I'm not quite sure where you are, but if you ever find yourself in England, do come and stay at my little cottage in North Wales. It can be a bit difficult during June and August because of what we call midges, little tiny biting insects which really, really irritate me. But at the moment it's just coming into summer in North Wales, and there's a most magnificent display of rhododendrons, red rhododendrons everywhere. It's very, very colourful. And for the first time the mountain hasn't got any snow on top, and it's a very good walk. If you want to go walking, come and stay in my cottage, or if you want to bring a bike, come and bring a bike. And that goes for you, Ragad. But I'm sure, Ragad, you've got better things to do than walk up mountains. I'm not sure. How are you, Ragad? How are you? Can you hear me, Ragad? Okay. I'm always picking on you, aren't I? I sort of make you an example of communications being sent to you and things like that. But Ragad, if ever you're in Britain, come to North Wales. At the moment, I'm spending quite a bit of time in the tiny little cottage we've got at the foot of Mount Snowdon. And it's quite interesting because the weather is very, very localized. So even though we might be having snow close to the mountain, then at the seaside, which is only 8 miles away, you can have baking hot sunshine and warm seas. So it's quite an interesting country of contrasting weather. Anyway, so what I'm going to do today, and we've only got a couple more sessions to go, unless you ask Michael and you can have some, in the case of Amma, because you started I think quite late, and especially Mustafa, if you need some more sessions, they can be arranged, no problems. Wherever you are, as long as you've got the minimum of a smartphone, and no matter where I am, I can actually help. I can give you a presentation or an explanation. So Ragad, it's good to see you. I haven't seen Ikram recently, but I hope she's all right. I think I've been in touch with her. Okay, so it is, I believe, the 4th of June, 2021. In other words, it's very close to midsummer here in England. What I want to do is to give a summary of the work that we did last week and the justification of doing that is simply, I'm just going to check to make sure. Okay, I've got a recording going, and I might try as usual, making an official recording, which never seems to work. I think we got one on towards the end of May, but not at the end of May, which I wanted to. And the reason I'm doing that, to summarise last week's work, is because it's important. Conceptually, it's very important because what we were dealing with was TCP, which is a critical network internet protocol, and it's important for computer scientists to understand how it works in some detail. And I've given you quite a long presentation on TCP. We haven't covered every single topic by any means, but we've looked at critical things like the three-way handshake. So hopefully that rings a bell. And subtopics like making a connection with TCP has been observed. You have an understanding of that. You have an understanding of the fact that TCP has got an element of flow control. It can control the rate at which it sends data. And what we were doing last week was to look at a particular aspect to flow control, because by means of operating with buffers on the receive side and the send side, then the receiver can simply tell us to decrease or increase what's called it's the transmit window on the send side. So for example, on the receive side there's a limited amount of storage available in the form of a buffer, and if the receiver feels that it's getting too much data or too much data too quickly, it can tell me simply to shut my transmit window down a little bit, and that'll have the desired effect. But last week we looked at something fairly sophisticated and fairly subtle, in the sense that the sender can actually learn what the state of the internet is as far as its communications with a particular receiver are concerned. So I'm going to read this presentation out, and hopefully I'll just make it clearer. I mean, I'll try and give you notes on everything I say. So last week we learnt that not only does the receiver in part control the rate at which the sender transmits data, but the sender can learn about what's happening in the general internet environment. So I don't know how much you understood that, and I don't understand, I'm not quite sure if you fully appreciate that, but I just want to say a few initial words about that before moving on. So firstly, last week we saw that on starting transmission, a sender, no matter what the receiver's advertised receive window size is, that has been communicated to the sender, for example, as part of the information contained in an ACK segment. So supposing the receiver's doing a routine acknowledgement of receipt of data, what it can do is to simply send me RWND, receive window size, an updated receive window size. So it could be double the amount of data that I'm allowing the sender to send me, or it could be half of that, or some fraction of that. And what the receiver do on receiving this acknowledgement will adjust its transmit window, adjust its sliding window. So hopefully you've got some understanding of how the sliding window mechanism works on the transmitter side. But the rule is that the sender is going to choose the smaller of the receive window, which is it's been advertised by the receiver. It's been sent to me, and what's called CWND, the congestion window. In other words, it's going to adjust the size of the sliding window to the smaller of those two numerical quantities. And you might say, well, how does that actually operate? Well, secondly, immediately after the three-way handshake occurs, right, so I'm a sender. I've established a connection with, let's say a server or a peer, and what happens immediately on wanting to send data, slow start occurs. Slow start. So remember, slow start occurs. Very first thing that happens. In which case, the congestion window size is set to 1. And it's highly likely that this figure, 1, is going to be less than the receive window that's been sent to me by the receiver, during either during the three-way handshake or routinely as part of the receiver acknowledging receipt of data that I've sent. Key thing here in slow start is that soon afterwards the congestion window will start to increase, and not only increase but increase exponentially, and the amount of data is going to increase. That's what I mean. And we'll be allowed to do so until the congestion window size reaches some threshold, and this is called the slow start threshold. And from that point onwards, so it's reached this provisional limit to how much the sender can increase the rate at which it's sending data. I mean, exponentially, so the first bytes, it's going to be one segment, then 2 segments, 4, 8, 16, 32, and so on and so on. That's what I mean by exponentially, an exponential increase. And so anyway, when the congestion window reaches this threshold, and I'm not going to tell you how the threshold is determined, and I'm going to keep that as a little bit of a mystery at the moment, but there is this threshold, and at that point the congestion window will still increase, but will increase additively. In other words, instead of doubling the amount of data I'm sending per unit time, I'm simply adding one segment, one packet, on each transmit occasion. So the rate at which I'm increasing congestion window slows down. Now, the other thing I told you was that there's no reason why I can't, as a sender, continue increasing the amount of data per unit time that I'm transmitting. I mean, I could go on for the next year and a half, logically, but there's a very high probability that as I increase the amount of data I'm putting onto the internet, I will get some form of congestion, busyness, inability for the network to cope with this amount of data. And I showed you two graphs which indicated what network performance looks like as congestion occurs. I mean, there's a big slowdown in what are called throughput, for example, and that's the amount of data I can successfully transmit. Right. So logically, what I'm saying is that, okay, at the moment I'm increasing the amount of data additively, not exponentially. But even in that case, there's a probability that congestion will occur. And it's going to occur, which is going to be convincingly underpinned by a timeout. And I'll explain that once again in a moment. Or more suggestively, in other words, it's not convincing evidence, but there's a highly likely indication that there is congestion by the receipt of 3 duplicate ACKs acknowledgements. And in both cases, the sender is going to respond in appropriate ways. So in the first case, for example, it's got a timeout, it's going to dramatically reduce the congestion window to 1 and enter a slow start phase all over again. In the second case, okay, so we've just got an indication that there may be congestion out there. What we're going to do is to halve the size of the congestion window. So I'm not reducing it to 1, I'm halving it. And instead of doing slow start, which is quite dramatic, I'm going to do a more gentle additive increase. And notice that 1 is a method for coping with congestion, and the second is a way of avoiding it. So you're going to have to think about that carefully. Why am I saying that? Let me just take a few seconds to explain what a timeout is. When we looked at the design of a reliable protocol, which seems to be almost a lifetime ago, but we looked at some finite state machines, and what we investigated, well, how do you get reliability in the case where maybe what I've sent to Mustafa is corrupt. Mustafa has got the option of asking me to resend the data again, and on this occasion hopefully the data will arrive, or Mustafa is actually expecting some data but he doesn't get it. So what he can do is to ask me to send the data again. And it's possible that the data didn't arrive, or the data became corrupt because of some form of congestion. Just incredible business out there on the internet. So the point of what I'm saying is that when I, Christopher Kinberg, send Mustafa some data, the moment I send him a packet, I'm going to switch on an alarm, which is going to ring a bell after a fixed amount of time. And if during that period the packet I sent has not been acknowledged, then I'm going to resend the packet again. It's a timeout. Now, the most likely cause of having a timeout, and let me say this once more, the most likely cause is simply the likelihood is simply the cause of a timeout is going to be the actuality of congestion on the internet. And remember, if a router, for example, has got so much traffic coming in that it hasn't got enough queue space to queue the arrivals of packets, it's going to drop one or more, and that will have a knock-on effect of causing the sender to time out, because it's the packet that the sender sent isn't going to reach its destination. Why? It's been dropped at a router, and eventually the sender will actually resend the packet that hasn't arrived. So that's a clear case of congestion. What happens in the case of a congestion? On the other hand, there is a possibility that a packet does actually go missing. It's a one-off event, and the next packet sent arrives at the destination, and a third packet sent is going to arrive at the destination. In those two situations, when I receive an out-of-order packet, taking into account that a packet is missing, I'm, maintaining knowledge of what arrives, which packet arrives when. If there's a packet missing, what I'm going to do is to acknowledge the first packet that was sent before the packet that went missing. So in other words, let's supposing I receive packet number X, and then I've been sent another packet, let's call it X plus 1, but I don't get it, and then I do receive packet X plus 3, and then I receive packet X plus 4. In the last two cases when I receive those packets, what I'm going to tell the sender is simply, I've received packet number X, and I'm actually expecting, but I haven't received, I'm next expecting packet X plus 1. Now, if the sender receives two such acknowledgements, saying the receiver is actually expecting to receive a packet X plus 1, what the sender will do is to automatically send out packet X plus 1. So I think I've given you a diagram of that in the main part of the presentation on TCP. So we've seen that congestion in the network affects throughput and delivery, so steps, if effective, so steps taken, if effective, are very important. And the fact of the matter is that in TCP, these two steps help enormously. And it's so I'm just going to, my conclusion is that we start off operating transmission of data using a congestion window, which is actually very small to begin with, but the size of congestion window increases quickly and quite dramatically. And when the threshold is reached, certain random threshold is reached that I've actually, it's not random, I've somehow scientifically estimated what the threshold should be. When that's reached, I slow down a little bit. I think the expression I used was I'm treading on ice. and I'm treading on ice very carefully. I'm testing the network out by simply adding one more segment of data each time I do a transmission. Okay, so I want you to, the reason I'm making a big deal of this is that at the moment I'm thinking of asking a general and a little specific question on network congestion as far as TCP is concerned. And if you're understanding the principle of what I'm saying, that's quite sufficient. Okay. So in addition, what we looked at last week was the nature of operating systems and the functions they performed, for example, in providing a GUI, a graphical user interface, or command line interface, but really command line interfaces are, I guess, a thing of the past. I mean, Bill Gates, when he first came up with an operating system, just offered a command line interface, which was very tedious to use. And the first versions of Windows, where he was trying to give a workable, usable human-computer interface to computer hardware, failed badly. It was awful to use and not very effective. But these days, sort of Windows 10 is quite usable. I mean, people would say that it's very inefficient and it's very long-winded, and because it's changing very regularly, it's quite hard to keep up to date with what it can do or how to change things if you don't like various aspects. And I gave you a long list of some of the functions of an operating system. I mean, the short description of what an operating system does, it's that it simply makes complex hardware very easily usable. Well, I can open a file and create a file containing my homework very easily, and I can edit it, and I can print it, and I can display it on the screen, and I can send it to you using Ethernet, local area network, or the internet using TCP. It'll have a major say in how TCP can be used and so on. So I urge you to do a little bit of investigation on the nature of operating systems yourselves, because I think the description I gave was fairly bland and very general. But to get something out of it, you should really do a little bit of, I don't know, maybe Google research or get a book from your local library on operating systems. There are some very, very good ones about. And at the beginning of this course, we looked at, I guess, device drivers in the form of a hard disk driver. And we looked at how reading and writing data from a hard disk is scheduled. And I think towards the end of last term, we actually had to look at how a CPU is scheduled. How do you put all the programs waiting their turn in your computer system? How do you place them on the CPU? What's the most effective way of doing that? Well, that's really the responsibility of a good operating system. It's going to choose an appropriate scheduling algorithm for your, I don't know, I mean, I met someone yesterday who's got 8 logical processor units on their laptop, and I was quite impressed with that. I mean, I've heard of quad core, but to actually see an octo core computer, it's very powerful, very useful. but it's made usable by an operating system. And there are lots of different operating systems in the universe, and it's probably worth saying that operating systems are appropriate not just to laptops and mainframe computers, but they're also appropriate to have if you've got a processor-based system running on your refrigerator, or you've got one running as part of your home security, or if you're actually building a self-landing module for what I hear America is just about to build, a new generation of supersonic aeroplanes. So the world of computing includes not just laptops, but little embedded devices, embedded systems. I mean, I've got a little, I think it was sold to me as a spy pen, so it can actually, it's quite remarkable, it can listen and whilst taking video clips of my surroundings. And it's just like an ordinary pen. I mean, it looks like a brand name pen, but it's chock-a-block with antennas and processors and little high definition camera. And it's quite impressive. And it was made in China, and you could buy it for, I think, £2 great British pounds. Incredibly cheap, quite interesting. Anyway, so I want you to do a little tiny bit of work on. I mean, I might set part of the coursework on just do a little bit of research on operating systems. Tell me something interesting about operating systems, something along those lines. So for the benefit of our newcomers, you need to understand most of the work on TCP covered as measured by our topic recordings, and you need to cover a document that I gave you on streams, and I've given you some very simple intuitive material on classes and objects, and the idea of a method being offered by an object and or a class, as this is going to lead directly to the idea of a socket which enables us to program the internet. I mean, I have no doubt in my mind that if you wanted to, you'd be able to use Java to transmit some data to a particular port on a particular laptop that's running in the Kremlin, if you had to. Or, I mean, I could give you an IP address, which is the IP address of a processor which is actually busy executing on a low orbit satellite. And you know, if you knew what you were doing, you could actually access some of the data. For example, the speed and the altitude and the direction and the actual coordinates of where the satellite is or was a couple of seconds ago, because the satellite I'm thinking about is quite high. No, it's not. It's a stationary orbit, so it's actually in a fairly fixed position above the Earth. So to conclude the course, you guys need to do some work, and I'm not pretending it's particularly easy. There's some challenges that are awaiting you. But what I mean by finding out what a class is, what an instance of a class is, and what a superclass is, what a subclass is, it's quite straightforward. Certainly from a mathematical point of view. I mean, you know, I'm not actually thinking about Venn diagrams, but I'm thinking about a definition of a class or an object, because you can create a copy, a specific copy of a class. That's going to be an object. You can create that using the keyword new, and I sort of expect you to not be frightened by object creation. And I wrote a very short, I think it was a Word document on just called objects. So take a look at that if you have any problem with that. And I should ask you about Razan. I've just seen your name. How lovely to see you. Welcome back.
Hello, sir.
Hello. I hope you've been working very hard, not only on your other exams, but on my subject too. But get in touch with me if you need some.
Yeah, I'm trying my best.
Please do. It'd be lovely to hear from you. Okay. So I'm pleased to see you. And I don't know. So I think so what I'm spent half an hour reviewing the work that we did last week, but hopefully it helps to make sense of what we were doing last week. And I remember students very often come and see me about 2 years after they finished the course, and they say, "Chris Klimberg, thank you so much for introducing us to this area. It's been so useful, and you know, look at the work that we're actually managing to do." And I mean, we're just looking at one aspect of computer science, and that's communications, and that's communications over the internet. So, but it's, you know, I argue that it's worth doing. But to do that, you need to use some Java and so on. So I first show you when I start this formal presentation, I'm going to show you two programs being executed concurrently. And you might say, well, what on earth are you talking about? But you know, we covered concurrency a long time ago, sometime in, I think, February. And I sort of defined concurrency as the apparent parallel execution in time of programs. You know, the simultaneous execution of, you know, it's like you and I both raising our arms. We're doing that in parallel. We can do that in parallel. We can raise that in space and time at the same time, you know, literally at the same time. Well, you can run programs on a laptop concurrently, and it's as though all those programs are executing at exactly the same time. And quite honestly, it doesn't make any sort of sense to say, well, which of the 8 programs that are running is actually running at the moment. You can't tell. It's impossible to tell, because it's a bit like Heisenberg. So if you're doing physics, you might have heard of Heisenberg. If you ask the question, you're actually altering the scenario, so you never actually get to the truth. You know, it's been and gone. Something else has happened. Right. So I've given you the code for these two. Sorry, it should be these two programs on Pharos, and I put them up on Pharos about 3 weeks ago, I think. One was a server and one was a client. Both were in using TCP, and I wanted you to execute both those programs using 2 instances of Eclipse. So in other words, you're using Eclipse to run the server and another copy of Eclipse to run the client. And I wanted you to do that, and I daren't ask you whether you've done that so far, but hopefully you have done that. You have done that now. And so today's session, in part, is going to pick up on the development of those 2 programs. I mean, what I want you to do Whether or not you understand the programs, it's just to run them and to use them. And you can type something on the keyboard, and a result from the server will be sent back to you at the speed of light, because it's running on your laptop. Both server and client will be running on your laptop. On the other hand, the server could be running here in North London, where I am at the moment, and you might be executing the client 2,000 miles away, and the programs will work. You can test the server and the client at home, wherever you are, but that doesn't mean that the server won't work if you run it in Nebraska in America or the South Pole. I guarantee to work. So I'm going to show you that. I mean, it's a bit boring, and you've probably seen the program already. So I might do that now. So let me. I'm just going to. I'm going to share an external video with you, and I've no idea. Let me try. I've no idea where the video. Here it is. I think. I'm just fiddling around. So I've got something called YouTube video. So I'm just going to execute a YouTube video made, I think it was made the night before last, very quickly. I just wanted you to see it. So I'm copying that, and let me just let me see if this works. So I'm posting that. Okay, I'm showing the video. So I don't know whether you'll be able to hear it or even see it.
What I have here are two Java programs. One on the left-hand side is a server. It's a UDP server. And the program on the right-hand side is a UDP client. And these are being constructed so that the client can actually send a packet of data to the server, and the server is simply going to echo it back. Not very exciting, but technically it's good stuff. And if only because if I send data to the server, then I could modify the server and do whatever processing of the data I want, and send a result back to the client. And the server and the client could actually be executing on opposite sides of the world. So what I'm going to do is to first of all run the server, and it's not actually giving me any information whatsoever here, but it could give me a lot of information, like which port it's listening to. Well, it's actually listening on port 7, but I can be told that it could also indicate what its IP address is. Well, it's actually the IP address of my machine, and the client is actually designed to, as I said, send a packet to the server, and what it's expecting is an echo of the packet I've sent to the server. So let me do that. So I'm going to run the client, and what's going to happen is that this line has just appeared, and whether or not you believe it, the client is ready to accept a line of text, and that's shown in green here, so I don't know whether that's highly visible to you. I'm going to press return, and what's going to happen is that almost immediately at the speed of light I get a message from the server, and it's just echoing what I sent to it. So I think this is sort of a reasonably good demonstration of the principle of UDP, User Datagram Protocol Services. And we're interested in the use of sockets to communicate. And as I shall explain in today's session, a socket simply can be regarded as an object which is assigned a particular port to listen to or communicate on, and the socket itself will actually offer methods to enable me to obtain an input stream and an output stream. And you'll find all that in the program. So I'm going to scroll through the program very quickly. And it's a bit tricky because DS is actually going to be the name of a UDP socket. And the socket's object offers me a receive method. Here you can see it. And what I'm going to receive is a datagram. And I've created the datagram so it's got some empty space, and I'm specifying the length of the space. So when I do a read on the socket, I'm going to read that much data into this array. So buff is being defined to be an array of 1024 bytes. And what I can do is to do a minimal amount of processing because I want to convert the data that's been received. First of all, I'm going to display the data received, and here it is. It was displayed. And then convert the line to uppercase. Well, in fact, it's already in uppercase. And then what I do is going to, well, it's a bit more complicated than that because I've built in a little randomized process to make sure that it's not going to send data back 100% of the time. It's going to send data back 0.6 times, in other words 6% of all the information it receives. And I mean, I've got commented these two lines out, but I can actually find out how much data, I could display the amount of data, etc., etc., etc. But what I'm doing is to simply to build a new packet for sending back to the client, and that's done by using creating a new datagram packet with all the data that's just been received. So SIN represents the data that's just been received, specify the length of that, and here in this critical line I'm sending the line of text back suitably converted to the client. So logically it's not all that complicated, but there's going to be some unfamiliar bits with you. And it's worth noting that the server is just operating in a while loop, so it's repeatedly waiting to receive some data, then sending it back out to the client again. And to every feature of the server, you can find a corresponding inverse aspect in the client. So I'm sending sending the server some data, and then waiting to receive it back. So hopefully you'll be struck by the fact that these two programs do actually cooperate, and it's a shame that this server isn't actually operating 3,000 miles away, just to illustrate the technological possibility of this. So I'm going to close that down now.
Okay. I need to make a very important point here, and it's that I'm just showing you a UDP pair of programs, and the reason for that is that we're going to have a look at UDP today. And the first remark I'd like to make is that UDP, unlike TCP, is unreliable. Alright, so there's no guarantee that a UDP packet sent to RAGHAD will actually arrive at that destination. I mean, it could go missing, and there's nothing we can do about it. UDP is very important, even though it's not reliable because it can be used to transmit audio and transmit video. Now, it doesn't really matter whether some packets go missing, believe it or not. I mean, there are technological ways of compensating for gaps in transmission. We can smooth the interruptions over if we have to. But the point of all this is that you can use sockets in UDP for transmission purposes. And a socket in UDP is very, very similar to a socket in TCP. And what we're about to do, first of all, so this is, don't get confused. What we're about to do, first of all, is to continue looking at the construction of a server and a client in TCP. And then, at the end of today, we're going to have a look at the structure of the UDP Internet Protocol. So hopefully, there won't be any confusions by the end of the afternoon, and hopefully you're going to find it sort of fairly interesting. So I'll tear down, I'm not showing video anymore, and I'm going to load up part of the presentation that you've seen already, and that is a presentation that's already on Pharos. It's called TCP Network Programming. So here we go. So it's going to take a bit of time to load this up. Hey, wait a minute. I don't know why I'm having to do this. So I don't need to do that twice. So I'm uploading the presentation now. And so it's loading quite quickly for a change, and you need to tell me. So you need to tell me whether you can see each page clearly. So I'm going to make this large. So I've deleted April 2021 because I think I first showed it you in April, and it's no longer June the 1st. It's actually June the 4th. So we've spent a bit of time thinking about this. We're just going to continue. So I don't know quite how much we did. Again, I set a couple of exercises. You probably haven't done them. Hopefully you have, but if you get the chance to, if you've got half an hour at 1 o'clock in the morning that you don't know what to do with, do it. So have a look at the programs. I think I've given you, forget about the week 10, UDP, we're going to look at UDP a bit later on. So, okay, so I'm getting confused now. The UDP programs I've actually shown you already were stop and wait protocols. In other words, they were quite interesting in the sense that the sender's going to transmit some data, and it won't be until it receives an acknowledgement back from the receiver before it sends the next chunk of data. So it's stop and wait, and I advise you to have a look at that. If you want to do any project work in the area, then you're welcome to do something on the simulation of stop and wait in UDP. But what we're doing this afternoon is to look at TCP, and I'm just pointing out the fact that we can use streams and readers to program all the input and output needed for an internet server and an internet client. And just to remind you for about the 20th time, a stream is just an endpoint that supports various methods for performing input and output. So a reader can be constructed from a very simple input stream. And what the reader will enable you to do is to read or access bigger chunks of data than available from a normal, simple input stream. And I know I'm going over this for, I think, the second time, but I think it's quite important. And what I've got is I can compose 3 streams and readers into one unit. And where the blue unit is, I can use that in Java for the purposes appropriate to reading a particular input channel. So I'm assuming that this red unit is a very simple input stream that's capable of just reading a byte at a time. And this unit here will enable me to read characters rather than bytes at a time. And the blue unit is going to give me methods for actually reading lines of data, like line of text, which is infinitely preferable than having to read, say, do a read 70 times to get one line of a file into the system. I'd much rather just read one long line in a single operation. So this is what we're here to talk about, TCP socket programming. And the idea, I'm giving you an overview background again. So first of all, the client must contact a server. In other words, it's a TCP client and it wants to communicate with a TCP server, like a web server. And what must happen right at the start is that the server logically must be running, must be up and running, and it must be listening to a particular port number, it must be listening to incoming requests for connections on what's called a particular port number. So the server must have created a socket that will welcome the client's contact. In other words, it's going to be a doorway by means of which we can perform a 3-way handshake, TCP handshake. And the client contacts the server by, first of all, creating a client TCP socket. So that's on the client side. What is a socket? It's simply an object that represents an IP address, a particular IP address, internet address, together with a port number, a remote port number. So it's going to be the server's internet address and the port number on which the server should be listening. I mean, we'll be in trouble if it's not listening. And what happens when we create a socket on the client side is that the 3-way handshake will take place. You know, and it relates to everything that we were saying right at the start of this talk, namely that amongst other things, receive window will be sent back to the client, telling the client not to exceed that amount of data on the receive side. So when the client creates a socket, the TCP establishes a connection to the server. And okay, so the tricky bit is this. When the client contacts the server, the server creates a new socket for the server process to communicate with the client. Well, what does that mean? Well, the socket will actually provide automatically 2 streams, 2 channels, as it were, which allows the server to send data to me and to pick up data, to read data that I've sent the server. So this is a sort of a byproduct of establishing a connection with the server. The server's going to create a brand new socket for me to communicate on. So in this way, the server can actually then go on to talk with lots of clients. And I think I mentioned, for example, a Microsoft server I think it's still based in Redmond, can support at any given time of the day 10,000 different clients. And it can talk to them concurrently. It's as though Chris Kenberg, is receiving as much attention that Mostafa is getting on his connection with Microsoft. Right? So again, I don't think I have to say this, but TCP provides a reliable in-order transfer of bytes. Great stuff between client and server. Right. So I'm providing two separate flow diagrams, but if you wanted to, you could convert these two very easily to an equivalent finite state machine. And on the left-hand side, I'm describing accurately the behavior of a server. It's very simple. Right. Create a socket, a welcome socket, which is it's something like, it's going to be, well, it's not quite right. I mean, the better Java version is this. And I can't actually, let me see if I can. I'm going to blow this up for my benefit here. So it says my sock is a new server socket with a particular IP address, and I'm listening on port 80, and a dedicated socket to communicate on an incoming client request is simply to accept a connection using mysock. So mysock is the server socket, and it contains a method called accept. In other words, I'm going to just wait for an incoming connection. When an incoming connection arrives, I'm going to create a dedicated socket to handle communications with that client. So what this does, I'm just waiting for an incoming connection. I get the connection. I can read a request by means of finding out which incoming stream is available on the connection socket, and I can write a reply to the client, again using a stream available from connection socket. Then I close. I've done. Finished. I mean, maybe just to pick up on something I said last week. I mean, maybe what I'm waiting for is a request to purchase some bitcoins, and get the request from the client, and I mean, maybe I'm going to take all the financial details down as well. Then I write a reply to the client, just saying, okay, it's all done, and here's a reference number, and I close. Finished. Right. So on the client side, all I have to do is to create a socket called client socket, and in fact, I'm going to connect to a remote port number that the server's listening on, and a particular IP address. So this is sort of general pseudocode. It's not precise Java at the moment. Once I've created a socket, I get a connection with the server, and at that point in time, I can send a request to the server, and the server's listening, waiting for some kind of incoming communication. Then it sends out a reply, and I'm waiting to receive it. And I'm using the socket I created for the client, and then I close. So another way of looking at and understanding this is that a client, using the three-way handshake in the background, talks to the server. The server accepts the connection, the request for a connection. It creates a socket on which the server can send data to me and receive data back from me. Okay, so remember that a socket is an object, and for our purposes it just contains information about the IP address and the port number, and two methods for returning streams for the communicator. Like, and the communicator might be a client, it could be a peer, it could be a server, in order to communicate on basic input or output streams. So again, I've just sort of exploded that diagram up a bit. What the client does is to create a socket. Dead easy in Java, one line of code. I connect up to the server process 3,000 miles away by establishing a connection on a particular port. If the server accepts that request, it's going to create a dedicated connection socket. Alright, so okay, so I want you to just concentrate here. Right. What I'm showing you in this diagram. So look at this sort of like squashed oval, this squashed rectangle. That's the client, represents the client. And all I'm showing here are the relevant streams. So I can get data in from the keyboard on this stream. It's called input from user. It's an input stream. So I can get data very easily. I'll show you how to do that in a moment. Right. What I'm going to do with that data is to immediately send it out on this stream, and I've called this stream out to server. So logically, the data I've just typed in at the keyboard is going to be sent out on the internet, 3,000 miles away. And 3,000 miles away, the server's listening to whatever I've got to say, and eventually the server will reply, but it's going to reply on this stream. So I'm going to construct this stream on which to receive data, and when I've got the data, I'm going to display it on my screen. So logically, there's nothing very complicated here, but let me, I'll answer questions in a moment. So in from user is a stream, and it sends to server. Okay, so I've given you everything you need to know about what things do. Just haven't actually shown you how to construct this stream. Right, this stream is going to offer me a way of reading data from the keyboard. Let's have a look at that. I'm sorry, I've got a telephone running in the background, so I'm just going to ignore that for a moment. So system.in is a stream connected to the keyboard, and I can harness that by writing this. So I'm defining in from user, and that's going to result from creating a new input stream reader, which I'm attaching to this very basic string called system.in. This is a system-defined input. It's connected to my keyboard. It means that a program can read the data I'm typing in. Right? And problem is that from this system.in, I'm creating a reader. And the useful thing about this reader is that I can use in from user, which is an input stream reader, which I've just created, to read in lines of data. It's great, that's all I need. Alright, so new input stream reader is going to be attached to my system.in stream, basic stream, very basic stream. But we're not quite done, we're not quite finished yet, because using the input stream reader, I'm going to create a buffered reader. All right, and it's that allows me to read in a complete line of data from the keyboard, my keyboard. And how do you do that? Well, you need to have a bit of an understanding of all these things, but this is the most difficult thing you'll ever come across with me in Java. You're going to create a new buffered reader from the result of creating an input stream which is attached to this basic stream called system.in. So logically, I'm building this object, if you like. Here's the basic system.in. This is the input stream reader. In other words, I can read characters. But the buffered reader enables me to read lines of text. So this black arrow indicates the direction of data being read. I can read bytes in from system.in. I can read characters, or I think it's arrays of characters, using an input stream reader. And if I create from the input stream this horrible coloured object, if I create this now, it'll allow me to read whole lines in from the keyboard. So you're going to have to think a little bit about that. But so what's the point of making this composite object? Well, again, I'm restating what I've just said. An input stream offers very basic input methods such as read, which returns an integer or a byte. Input stream readers, on the other hand, take an input stream, basic input stream, and give you a reader, which offers you new methods. For example, you can read characters, and so you should really refer back to my earlier document on streams if you want to know what some of the streams are and how they're used. It's just called streams. So we'll show how an input stream can be converted to a reader for easy character reading without using. Okay, well this is just, you can read this in your own time. Here's a little program, and I'm taking, what am I doing? Look at IS here. That's attached to my keyboard. I'm creating something called an input stream reader from the input stream, and I'm calling it reader. And then from reader, I'm creating a new buffered reader from the reader. And the result of all this is that I can actually read a whole line. Look, here's a method. Here's the buffered reader, buffer reader, dot read line. Read line can read a whole line of text. So name is a string variable, and I'm reading a line of text into that variable name. Don't worry too much about that. Okay, but how do we build a stream to connect to the server? So this is critically important. I want to build this stream which allows me to use methods to send data out onto the internet. That says to the network. This is going to go to the server out there on the internet. How do I do that? Well, it's very similar to the foregoing. What I'm doing, I'm creating a stream. It's actually a data output stream. So you're going to have to find out exactly what a data output stream offers by way of methods. Okay, so this new stream is called out to serve. It results from creating a new data output stream from an output stream that I can obtain from my socket. Look, here's the name of a socket, client socket, dot, here's the method. This is going to return a very simple output stream. It's going to, the actual client socket would enable me to write bytes, But a data output stream is actually going to allow me to write arrays of bytes. So this time we're going to use the data output stream. It's going to enable it gives us a method called write bytes, so I can write an array of bytes to send data out, which is handy. It's what I want. So first of all, remember that given a socket such as client socket, so that's client socket, that's the socket I created to connect to the server, returns okay, so client socket dot get output stream returns the output stream that I get when I create a socket connected to a server. Give this to the data output streams constructor to again build a composite object, a composite stream, which you can think of as looking like this. I've got an output stream, and so what am I doing here? Data output stream. Okay, so using this, simple output stream available from the socket that I've used to connect to a server, I could send out bytes, 1 byte at a time. Useless. I don't want to have to send 100,000 bytes, each one in turn. I'd much rather send bytes as a very large array, all in one go. That makes sense to me. And I think we had a bit of a discussion last week about silly Windows streams. I don't want to have to send 1 byte at a time if it requires 40 bytes to send it in a TCP packet. I'd much rather send a header, a single TCP header, with say 2,000 followed by 2,000 bytes of data, which represents characters and that I'm sending to the server. Hopefully all what I'm saying makes some sense. How do I get data from the server? Well, very similar. I need an input stream to get the data from the network. How do I do that? Well, this time I'm using an object called in_from_server, which is a buffered reader. Why am I choosing a buffered reader? Well, it means I can read a whole line of text from the server at a time. How do I do that? Well, I create a buffered reader, but I'm attaching that to an input stream reader, which itself is now being attached to the simple input stream I get from the original client socket. So it looks horrible, but you can, if you want to, just simplify it a little bit. So you could think of this, I've broken that long line up into 3 chunks. So have a look at this. It's a fearsome line of code on the face of it. Break it up into 3 bits. First of all, temp is the result of obtaining the input stream from my socket. And then I put temp, add it, attach it to an input stream reader, create an input stream reader, that's called temp1. And then finally, I attach a brand new instance of a buffered reader to temp1. And that'll enable me to let me demonstrate this. So this is the client, and I got a sentence which is of type string, and I want another variable called modified sentence, which is going to be the result of having processed or having sent the sentence to the server and having received a processed sentence back from the server. So how do I do all that? Well, first of all, I'm going to create a client socket. So it's a new socket, it's a TCP socket, server name, or the server's IP address, and it's listing, I'm assuming that the server's listing on port 6789. And I create an output stream attached to the socket. So out to server is an output data stream attached to the basic output stream attached to the server out there 3,000 miles away. And I can create another stream in from server in an analogous way. So I'm getting an input stream and then changing it, modifying it to get a buffered reader. And then guess what? Look, we nearly finished the whole program. The string variable sentence is going to assign the value of having read a line from the keyboard, and then I'm sending sentence out as a sequence of bytes on the out to server. I think it's a data output stream. And then look at the next line. Modified sentence is going to be assigned the result of reading a line from the server. So input from server is connected to the server. It makes available a method or a function, if you like, or a procedure called readLine. Get the line, store it in modified sentence, then print it out, then finished, done what I wanted to do. Very straightforward. So how to build a server? You get all the corresponding operations, but you don't have to read the keyboard, of course, but what you've got to do is to write the result. What you've got to do on the server side is to read an incoming stream and then write the result of modifying the data back to the client, and do that repeatedly, I guess. So I'm going to outline this fairly quickly, but listen carefully, right? Here's class TCP server. So this is a complete program, and I've given you this. I'm sure I've given you this on Ferals. So run it, and then spend some time trying to come to understand it on the basis of all the work that we've done on TCP. So class TCP server. This is the main part. So it's public static void main. This is the main part of the program. Two variables, client sentence, which I'm going to read in from the keyboard, which I have read in from the keyboard ultimately, which I've received from the client, and then I want to send back to the client the result of processing that sentence. And all I'm doing is to capitalize the sentence I've received. So here we go. I create a server socket. So, okay, you don't know what a server socket is? Look it up. And you'll find a description corresponding to what I said the server does. It listens on a particular port. If it accepts a request, it's going to create a dedicated socket for you to listen on. Right. So, while true, in other words, repeatedly, forever, a connection socket is the result of accepting a connection on this socket, welcome socket. And I'm using a buffered reader to receive data from the client. So back to this buffered reader. I mean, this is going to be the buffered reader over here. It enables me to read a chunk of data, namely a string from the client over the internet. And then, well, guess what? What do I, I'm going to capitalize this sentence in a minute. But then I want to send it back. So how do I do that? Well, first of all, I define out to client. So this is going all the way back to to the client across 3,000 or 5,000 miles or 11,000 miles, whatever. This is the formula for doing it. And what I'm doing here is I read a line from the incoming buffered input stream from the client. Then I'm going to change the sentence to uppercase. And okay, well, we haven't looked at all the operations you can perform on sentences. But a sentence is a perfectly good object, and it offers lots of things, like you can change a sentence to uppercase and so on. So just take this on trust. And then, okay, so I've got as a capitalized sentence, and that, I guess, should be joined together, no space here. What I can do is to write the capitalized sentence back to the client. How? Well, I use out to client, the out to client data output. Is it a buffered? No. Output. Out to client is a data output stream. And I've got a loop. Look, here's the end of a loop. Where does the loop start? Let's just check that out. I've got a while loop here. Look, while true, I'm doing all this. I repeatedly accept connection from a client, read the data in from the client, capitalize it here, change it to uppercase, then write it out, and then start all over again. Wait for another client connection. Okay, so hopefully the way in which I presented the construction of both a server and a client really depends on your coming to understand how you actually can build data output streams or buffered input streams from a simple input stream. And I'm going to leave that to you, and I've written about it in my notes on several occasions. But I think I said I was going to give you some ebooks, which I don't think I have yet, but hopefully you've got some text that you can look at immediately on Java. And if you haven't, I'll make them available. I mean, I've got 4 or 5 books I can make available to you. All right, so I just want to finish off talking a little bit about high performance servers and some of the issues. And I guess socket operations can cause a process to block. So, for example, accept means waiting for a new connection. So the server is actually going to suddenly come to a halt whilst it waits for Chris Kimberg to request a connection with it. And it takes time to read a socket if I'm having to wait for data to be sent to me. I mean, it could, how much data is being sent to me? It could be a lot. It's going to take time. Or maybe if I'm writing data out onto the internet, maybe I just need lots of space to send that data, and so on and so on. So, crucial aspect of network server design is to do with concurrency, and it's to do with non-blocking. I don't want things to block if I want high performance. I don't want to have to wait for space in order to send data out. I want to avoid any kind of denial of service. I don't want you to have to wait to get a chance of using my server just because I'm having to spend a lot of time sending data to one of you guys. I mean, if you're busy serving me, and everyone else is going to work. The concurrence is also very important for clients, and to write a high performance server you need to go the multi-threading route. You need to think about concurrency. Okay? You need to think about concurrency. Okay, well, I was just about to take a very short break, but I won't. So, let's assume that I'm a server and this little horizontal ladder indicates a queue. So I've got a queue of requests from the internet, and they all want to buy bitcoins from me because I'm offering a dubious discount on bitcoins. And what happens is that a process called the dispatcher will look at the queue of incoming requests and create a thread, thread number 1, to deal with client number 1. And then almost simultaneously, the dispatcher is going to reach into the queue and take out the second process and create a second thread to deal with client number 2 concurrently, and so on, and so on, and so on. So in the steady state, maybe I've got 5 clients being given attention to. And maybe you've got n clients, maybe n is 1,000. I'm dealing with 1,000 different clients. And I'm sending the results obtained. I mean, it depends what each client wants. But I can actually send out all the results back out onto the network. Okay. Okay. Let me just leave a. Let me just. Okay, so I'm sending Mustafa. Alright. Oh my, typing. Anyway, so here we've got another appearance of the importance of being able to program concurrently. And I might, before the course finishes, just show you how to create new threads to deal with new clients. And remember what concurrency means. It's as though, to all intents and purposes, that the clients are being dealt with in real time, in real parallel fashion. And this is all made possible by the fact that if you've got a 3 gigahertz machine, you're capable of executing many hundreds of instructions per process that's dedicated to dealing with a client for all the different clients that you're dealing with. So it's just to appreciate that it's actually straightforward. Instead of okay, I mean, I'm just going to backtrack a little bit. I mean, just let's go back to let's just go back to this flowchart, wherever it is. I'm going to have to go quite a long way back. I want you to notice one feature of this diagram, what does the server do? It repeatedly waits for a request from a client, deals with it, finishes dealing with it, and then and only then it goes back to wait for a second client. But my question to you to think about is, well, during the time that the client's being dealt with, which is represented by the movement of my cursor from here to here, surely I could have dealt with a second or third or fourth or fifth client if I'm doing these steps in parallel with those for any other client. So, ask me if you think that's, doesn't make sense, or you don't understand that. I'm telling you the truth, right? And I might as well just mention one other thing quickly in passing, and that is Java's NIO, new input and output, which is non-blocking. Okay, so if you're an internet engineer and you want to look at very high performance servers, which are good, it's a good thing. I don't want to have to wait half an hour before I get any kind of attention from a server of input. I mean, if I'm working in finance, I want very rapid responses. If I want to sell my stocks and shares, I want to sell them now, not in half an hour's time. So Java's NIO comes to the rescue a little bit, and I don't think we've got time to dig deeper into that, but I just want you to realise that it's available. Okay, so it's now, we've got about an hour left, and I'm literally going to take 2 minutes off because I've got to pass someone a telephone. So please, just bear with me. I haven't disappeared. Okay. Hello? Hello? Okay, do any of you have any questions or comments about what we've done so far? Mohammed, Mansour. Oh, Mansour, hello. Just seen you. All right. It would be very nice to have 8 webcams on. And I'm just wondering whether I can turn my... This is me, by the way. So that's what I look like, in case you haven't seen me. I'm afraid I've got a bit of a lockdown haircut, but I've got this wonderful movable webcam that in principle can actually point at anything. Any questions? Mansour, Mohammed, Mustafa, Ahmed? No questions. Sure you do.
Yeah.
Well, if you have a technical question, let me have it by email. Raghead, any comments before we start looking at UDP? And then I guess once we've done UDP, we can really relax and think in terms of, well, Kinberg has actually done most of what he wants to do with us. Raghead, any comments? No. Okay. Right. Oh, you are there. Any comments?
No, all clear.
Are you sure?
Yeah.
All right. I believe you. You're a very clever lady, so I believe you. All right. And whilst we're talking, I mean, you've got both your coursework results back, have you? I've given you 2 coursework results. Have I? Anyway, so, but guys, as I said, I'm going to, this is what I said right at the beginning of the session, I'm going to issue some coursework. I'm deliberately making it as straightforward as possible, but still giving you the opportunity of showing your understanding. And I recognise the fact that I think one of you will have a unique assessment because of the time in which you joined the course. But I think it's Ahmed and another young lady who joined very late into the course. I mean, I want to assess you very fairly, and it'll just be on the basis of a reasonable expectation I have of the work that you can reasonably do from when you started all the way to the finish. But you will have missed, Ahmed, you will have missed a lot of the work. I mean, you've missed about 10 weeks' work, so I can't, reasonably expect you to be able to do everything. Anyway, I'm going to get rid of this. You've got a video recording of everything I've said today. I don't know what that is. Oh dear, that's a bit embarrassing. I'm going to upload presentation on UDP. So I've probably got the number completely wrong. It's not week 11. Not sure what week it is at the moment. I've given you a copy of the TCP programming, given you the copy of the TCP client and server. I'm going to give you, if I haven't given it already, of the UDP client and server by way of contrast. So what I want to do now is to talk about the UDP program. So yeah, I'm getting a bit. Okay, so I'm uploading that now. And do let me know if it's not clearly visible or part of the slides is missing. Sorry, I'm still stuck with that. So I'm going to. So I'm not sure where the presentation's gone to. Let me have another look. Sorry. I think it's on its way. So I'm going to have to start all over again, so I'm just to upload. Yeah, well, this time it's the PowerPoint's being converted, and it's being processed very quickly, so it should make an appearance fairly soon, hopefully. And if it doesn't appear, I shall log out. Oh dear, oh dear. So nothing's happening. So I'm going to close the presentation. Apologise for the wait. There's still nothing. Just give it a little bit of time. Nothing. Just bear with me. Just take. I'll try and sort this out. Just give me 5 minutes, please. Thank you. I'm trying to reprocess the PowerPoint at this end again, but we'll see what happens. So let's see. Try again. Oh dear, oh dear. Okay, so back again. There seems to be two of me. So I'm going to try.
You are now muted.
Okay, can you still hear me? Can you still hear me? I'm assuming you can. Right. The acoustics are really odd this end. Let me send you a text message. Anyone hear me? Okay, that's great. Okay, well, we'll just spend about half an hour looking at UDP. That's great. I mean, listening to my own voice, I sound as though I'm talking like a Martian. Okay, so user datagram protocol. I can give you a chapter in Foruzan's textbook if you want, but you'll have to let me know. The reading I'm giving you through these slides is quite adequate. But the version of the slides I'm giving you, I see that the format has been upset a little bit. Anyway, the intended outcomes of this session is that when we've been through it, you'll be able to explain what is meant by process-to-process communication. You will be able to explain the format of a UDP user datagram, and you will understand the operation of UDP, have an understanding of when it's appropriate to use UDP as opposed to TCP, and possibly have an understanding of the architecture of UDP UDP modules. Okay, the only problem with this is that I don't seem to be able to turn the pages. So, guys, I mean, considering the difficulties that I'm experiencing at the moment, would you prefer it if we continued next week? How do you feel about it? This is 2008. I mean, we've been going for 107 minutes. I mean, would it be okay if you accept a reduction of half an hour in today's session? Okay, well, what I'm going to do is to end the meeting and log in again.
You're currently the only person in this conference.
Hi, Ian. Mohammed, you're the only person I can see at the moment. Okay, so what I shall do is to... I think everyone else has just given up and gone. What I shall do is to record a standalone session on UDP, and I'll make that available to you within a couple of days. Mohammed, are you okay? Ahmed, you're back. Hi. I mean, I shall tell Michael that I was forced to abandon the session for the last half hour. But Ahmed, to repeat what I've just said to I think Mohammed, most of us here as well. But do you want me to continue? Can you hear me? Just for half an hour? Okay. Thank you, Mohammed. Right. So let me try uploading the presentation once again, and so I'm uploading. See what happens this time. If it doesn't work, I shall definitely abandon this. It should be fully uploaded. Okay, here we go. And this is the intended version. It's apart from the date, which is 2018, everything seems to be okay, and I've got control over the pages. So UDP, what is it? What's it all about? Let me show you. Forget that, that's not relevant. It's very much to do with the protocol stack. We've had a look at the protocol stack in connection with TCP. At the top level of the stack, we've got the application layer, and we've got the transport layer, which includes TCP and UDP and a lot of other things. And beneath that, you've got the network layer. So, and beneath that, you've got the data link layer, and at the very lowest level, you've got the hardware layer. I mean, it's like fiber optic communications or wide area network or local area network technology. And what I mean by a stack is that the application layer needs the services of the transport layer, and anything on the transport layer needs the services of the network layer, and the network layer needs the hardware data link layer to communicate data. So UDP occurs at this level, and what's actually going on here is that an application like, I mean, maybe, I don't know, something like VoIP is actually going to use UDP, and then UDP packets are going to be put into IP packets, which are then transmitted out over the internet. So we've covered a lot of all that. And here we are again, UDP server Java. So I've got a UDP server, which I showed you the video clip right at the beginning of the session. Not quite synchronized with what we're doing right now, but it's there. And using UDP is delightfully simple, and we can actually what am I doing? Server socket. Okay, well I might have some kind of, it's not a TCP server socket, but it's like a UDP server socket. Created a server socket which I want to send you, the client, some data. How do I do that? Well, there's a method called send, and I can send out a packet, and the packet is going to consist of an array of bytes or something along those lines. So a UDP server has a send method, which is an integral part of a socket, a UDP socket. And it's easy to use because all I need to do is to pack the data into an array and send it out. I'm actually sending it as a UDP datagram, which I'll talk to you about in a moment. All right. So if I'm sending data from A to B using UDP down the stack, across the internet, back up to the receiver, and I can identify the particular application running on B by means of its UDP port. So the sender is actually going to specify an address of this machine here and the port on which the application on this device is listening to. So logically, that's not terribly complicated. Structure of an IP datagram, I'm sure you're asking. It's probably a bit simpler than a TCP datagram. So this is, not last week. IP datagram consists of a header and data. 20 to 60 bytes for the header, up to 65536 bytes, including the header for data. Right? And what an IP packet or datagram contains is an identification number, a source address, sender's address, and the destination address. So we've got a whole session on that. We spent about an hour and a half on that, not several weeks ago though. Okay, this is where UDP occurs on the stack, on the what's called the Tcpip protocol suite. Here's TCP, here's IP. IP is used to carry TCP packets, used to carry UDP packets, not both, one or the other. And so that shows you the structure of the stack, more or less, anyway. So IP headers, protocols, don't need to know that at the moment. Process-to-process communication. Before we take a deeper look at UDP, we must once again remind ourselves what host-to-host communication is. So maybe for 5 marks in your assessment, I shall ask, what is meant by host-to-host communication, and what makes it possible? So, see diagram on slide 39, which I'm not going to look at the moment. What we're going to talk a little bit about now are port numbers and socket addresses. Both are vital concepts, not only in the UDP context, but in the TCP context as well. So TCP/IP suite specifies 2 main protocols at the transport layer. So remind yourself what the transport layer is, what that involves. And the diagram that I've shown you shows its relationship with other protocols and layers. So for example, the UDP lies between the application layer and the IP layer. So in other words, I might have an application that wants to send you some audio, and I might choose deliberately to use UDP. Can I ask you a question that you should be able to answer now? Why would I use UDP rather than TCP after the discussion of slow start? I mean, the slow start for TCP means that the initial phase of data communication is actually very, very slow. And that's not good news if I'm showing you, if I want to transmit video or audio. I don't want huge gaps between clips of video that I'm sending you. So I might want to use UDP. Transport layers, so I'm telling you a little bit about transport layer. Several responsibilities. One is to establish process-to-process communication. And the most important device that it uses for this is to use port numbers. And in the case of TCP, it provides some sort of basic control flow mechanisms. But apart from UDP, the transport layer also provides a connection mechanism for the processes. So, sorry, this is all slightly out of date. UDP does not offer connections between two systems A and B. All it does is to send out what in effect is logically discrete packet of data to its destination. It doesn't remember what it's just sent. It has no idea whether what I've just sent gets to you. Couldn't care less. My job is simply to take perhaps video data or audio data, pack it into a UDP datagram, put it into an IP packet to send over the internet. Remember, IP is a general workhorse. You can embed other packets inside an IP packet, internet packet. Right. So the idea is that in the case of TCP, we're establishing a connection, and we send a total amount of data. When it comes to TCP, in chunks which are numbered, and I send them out one by one, and if one doesn't get there, I'm going to resend it. We know that from the earlier discussion we had. Right. At the receiving end, the transport layer will wait until all the different units for a TCP process have been received, check and pass those that are error-free, and deliver them. And then the connection, the TCP connection, is closed. UDP doesn't do any of these. It can only receive a unit from the process and deliver it unreliably to the receiver. So if I've got a process using UDP, I give some data to UDP. UDP packets it up into what's called a datagram, and does its best to deliver it. But the chances are it's going to be unreliable. Why? Well, there's congestion on the network. So technically, you need to remember this, UDP is connectionless, it's unreliable, and it adds nothing to IP apart from this single factor. It provides the mechanism for providing process-to-process communication instead of blunt host-to-host communications given to us by IP. If I've got an IP address, I can use an IP packet to send data to another machine. But I can't talk specifically to any processors, like you might have a time of the day process running on your machine, or you might be offering a stock market update on particular prices. I can't communicate with that using IP alone. But I could with UDP, because it provides a mechanism for talking to a particular process that's identified by its port number. So why use it? Simple. It's got minimum overhead. It's good for any purposes where reliability isn't critical. It's great if a process wants to send a sort message to a recipient. Why? It takes much less time to communicate than using TCP. If you were sending a short message using TP, you've got to go through all this slow start business. It takes time. Too late. Won't get there in good time. So why might unreliability not matter? Well, we didn't talk about it last week, so I'm lying here. Wasn't raised last week. As a network layer protocol, IP can be used to communicate between hosts. That's the key message. But the message still needs to be handed to the correct process. Well, how? Port numbers. That's the answer. Here. So we're using, got lots of processes running on this machine here. One of the processes wants to talk to this particular process. How do you do that? Just the particular port number which this process is listening to. Right. Few ways to achieve process-to-process communication. The most common is through the client-server model. Both processes have the same name, for example, daytime client or daytime server. Of course, a machine can support several hundreds of servers running at the same time. Local and remote hosts are all defined using different IP addresses. And to define particular processes, we need secondary identifiers called port numbers. So there's a server, a well-known server called www.time.gov port 13. And port 13 is a well-known port for time servers. Here's an example of a particular time server. And I might want this client, which is using port, I think 52,000, wants to find out the right time, so it sends a request to the time server based on this website, port 13, and I can actually receive the time of the day back, and then the client can actually display the correct time. So it's all done by port numbers. Port numbers select one amongst all these processes running on this machine. This is the IP address of the machine. This is a particular port number. So the address, the actual total address for this process is the IP address together with port 13. So in TCP, port numbers can range from 0 to 65535, which is obviously 2 raised to the power of 32 minus 1. The client defines itself with a port number chosen randomly by UDP on the client host, and it's called an ephemeral port number. And the server process must also define itself with a port number, but it's not usually chosen randomly. There are what are called well-known conventional port numbers for particular types of server. They're called well-known port numbers. Right, and some exceptions to the rule. Okay. So the Internationally Standards Organization specifies that ports between 0 and 1023, so the first 1024 ports are well known. You can register any one of these ports if you want to, and the ports higher than 49152 are dynamic or private ports. You can use them, or they might be dynamically allocated by your operating system. So a little bit more of information, which I'm just really repeating myself there. Here are some examples of well-known UDP ports. There's 7, which is echo. You can send something to UDP ports 7 with a UDP program, and you'll get an echo back. Or I can send a lot of nonsense to port 9, and that'll be discarded. I can interrogate port 11, and if it's a Unix machine, it'll return the details about who's using the Unix machine. Daytime looked at, quotes, port 17, it's quite interesting, you get quote of the day. Port 53 UDP is a name server, it's actually DOM name service, so in fact I could actually use port 53 to do a lookup on www.champignon.com, and it'll actually return the IP address of that URL. Port number 69 will enable me to transport files using UDP, etc. Network Management Protocol, SNMP, NTP, port 123. You can find out. I think again I can get network time and so on. So there's a lot of them, and you go all the way up to first 1,000 or so port numbers, all well known. So definition, finally, a socket address is the IP address together with the port number. IP followed by port number. Okay. IP followed by port number. That's a socket address. It's a socket address. So what about the size of a datagram and a UDP packet? Fixed size header, 8 bytes. Here it is, 8 bytes. Right? 16 bits for the port number from which you're sending a UDP packet. 16 bits for a destination port number. Total length, 16 bits of the size of the datagram. Alright, so 8 bytes for this chunk here, the header, and you can specify using 16 bits. That's 2 raised to the power of 16, thereabouts. Data that you can send using a UDP datagram. Okay, I'm just repeating myself there. And again there. God, yeah. So the length of a maximum length of a UDP datagram is 65354. Yeah, take away 8 for the header. That's the maximum amount of data. Yeah, so that's 65535. I think that's right. 65507. So check my reasoning here. Don't need to specify a length field in a UDP datagram because we've got a field defining the total length. So that all makes sense to me. When UDP gets the datagram, the IP header will have been dropped, and you've got something called a checksum, for those that haven't heard the word before, used to detect errors in the entire datagram. Very basic. Okay. Don't need to know about checksums for our purposes. So a little bit of information. Sorry about the CCM 2412 topic. It's an IFG topic. And what this section covers is connectionlessness, flow and error control, encapsulation, decapsulation, queuing, multiplexing and demultiplexing. I mean, you can multiplex packets by putting one inside the other, using one protocol to carry the other. So I'm going to finish here because it's 22 minutes past 1, and the last 20 minutes or so has been a bit messy, I'm afraid, because of the technical failure to swap to include my presentations. Right. So here I've got a process. So it's a running program, and it could be a distributed editor, or it could be something like a UDP based Zoom application, and I want to send some message to the other side of the earth, other side of the world. I'm going to put the message in the data part of the UDP datagram, and then I'm going to fit all this into an IP packet. So IP contains a destination IP address and a sender's IP address. The UDP header doesn't have anything of the sort. It doesn't tell you what the IP sender's address is or the destination address. That's now packed into an Ethernet frame, possibly, which has its own header, and it's transferred from my machine, perhaps wirelessly, perhaps by means of an Ethernet cable, onto a routing device, and it'll be sent over the internet to the specified IP address, and it's received, and the IP data is going to be extracted. It's discovered to be an entire UDP packet. So the actual UDP data in the UDP packet is extracted. You get the original message sent, and you pass that to the waiting process. Okay, so I'll stop there. And you guys, thank you very much, Wagad. It's good to see you here right until the very end. And I'm just going to leave you with an invitation, and that's and I think I issued an invitation for, you probably heard, I mean most of you were probably the people that I spoke to earlier. If you fancy a trip to a Welsh cottage sometime next when you're in the UK, just let me know. And if you want to do some mountain climbing, let me know. Alright, it's does you a world of good. Okay, so take care, and be prepared to receive coursework, and as I've promised, it's going to be fairly straightforward, apart from it is great, I promise you, and you can go horse riding, or you can tickle sheep, or if it's in winter, if you went in winter, you could borrow some ice axes, do some dangerous sports, and it is lovely. And I'm just wondering whether I can actually I can't do it. What I'll do is to show you a photograph of the mountain next week. So I look forward to talking to you next week. Take care. But the important invitation to you is, talk to me if you want me to. If you want to tell me something, or you want advice, or if you want an explanation of anything we've covered. So Ahmed, Mohammed, Mustafa, and Ragad. See you next week, and I'll put on the recordings I've made I put them onto what's it called? The virtual learning system, and I mean, again, I'll just mention the fact that I do keep an eye on the number of people who've looked at videos. I mean, there's variable quality videos, but some are worth listening to, some are really worth watching. And there's a minimum number of people looking at the videos I make for you. But all the best to you anyway. Bye bye. Take care. So I'll close the session now.